Hello. Today I want to show you what happens when you multiply two sine waves that are close in frequency. So here I have two different sine waves that are close in frequency, and this is their product. One of the sine waves is being generated by this Weinberg oscillator, which I built myself. The other sine wave is being generated by this signal generator. I just set the Weinberg oscillator to a random frequency, and then I matched it with this signal generator. And I'm multiplying them with an AD633 analog multiplier. So here's the theory. We're multiplying two sine waves of frequencies omega 1 and omega 2. Here I replaced omega 2t with omega 1t plus phi. So this phi is going to be a linear function of time. If we actually solve for phi, that's exactly what we get. It's a linear function of time, therefore its derivative with respect to time is constant. Omega 2 and omega 1 are constants. And that's kind of what we see here. The phi is just the phase difference between these two sine waves, and we just saw that it's supposed to be changing at a constant rate, assuming that these two frequencies are constant, which they are. Okay, so then all four of these expressions are equal to each other, and this expression in particular is very useful because here we have two sine waves. Here we have an expression with two sinusoidal functions that are functions of t. Here we only have one sinusoidal function of time. The other one, this sinusoidal function is just a function of phi, and this is actually the DC offset voltage that we're seeing. So let's have a look at the product. So again, this is the product of these two sine waves. You can see it's sinusoidal. It appears to have constant amplitude, which it does. And it has a time-varying DC offset, which if you look carefully, corresponds to the phase difference between these two sine waves. And without even looking at the math, you should be able to guess the DC offset as a function of phase. Is it sine or is it cosine? Well, when the DC offset is at its maximum, the two sine waves are in phase. There's a 0-degree phase shift. So, so cosine of 0 degrees is equal to 1. And cosine of pi is equal to negative 1. And you can see when the DC offset is negative, we have a 180-degree phase shift. And it crosses 0 when we have a 90-degree phase difference. That's a little harder to see because if you know anything about calculus, the maximum rate of change of a cosine wave happens when it's equal to 0. So let's slow this down. So now it's much easier to see. It's changing slowly. I'm also measuring the voltage of the output. So this is the DC voltage. You can see it's reaching its maximum, about 100 millivolts. Now it's reaching 0 as the DC offset reaches 0, right at about 90-degree phase shift. Now it's negative 100 millivolts. So that pretty much explains this formula, except for the fact that it's 2 times omega 1. That's also pretty clear, right? Because obviously this is a different frequency, and we can measure that frequency. So let's pull out the calculator. Here we have 23.74070. divided by 11.87036. Wow, that's exactly 2. So here it is. There's a lot of there's a lot of frequency shift mainly because of this. My Weinberg oscillator isn't very good mainly because of this potentiometer. I don't know, I forget what exactly the material is, but I suspect it's carbon, or it's garbage. It has a really bad thermal coefficient, so like if I touch it, the frequency is going to change a lot. So we can actually measure, we have a frequency counter. Let's look at the phase stability of, first of all, the signal generator. No, first of all, the Weinberg oscillator. Hello? Oh wait, no. This is the signal generator. So you can see it's very stable. It is very stable indeed. Now let's look at the Weinberg oscillator. What? It's saying that it's stable, but it's not stable. Oh, here, it moved. It was moving a lot more earlier. I guess the temperature stabilized or something. Oh no, here it's going. Maybe I'm breathing on it. Hey, there we go. There we go. You see, that's what I'm talking about. It's absolutely horrible. Okay. Also, it's microphonic. If we look at it here, because I'm using an incandescent light bulb for automatic gain control, when I drum on the table, you see? That's because the light bulb is microphonic. So that's also not good. Look at this. Look how much drift we've had. So here we go. We got it back. The last thing I wanted to talk about is that using this formula, using this formula, we can derive this formula just by plugging in phi. And this is useful because it shows us that multiplying two sine waves generates some linear combination of sine waves with two frequencies that are the sum and difference of these two frequencies. And the important thing to note is that cosine is an even function, so it doesn't matter which, even if this is negative, the absolute value of omega 2 minus omega 1 will always be the same value, right? And cosine of negative x is equal to x, so that works. Oh yeah, and this can also be used to visualize this, right? So, because here, essentially when the two sine waves are very close in frequency, one of the components is going to be very close to DC, and that's why this formula works, right? So it's like a DC offset. For a constant phi, it is DC, and for a time varying phi, it's a frequency, this. Yeah. And then we have the omega 1 plus omega 2, which when they're approximately the same yields twice omega 2. All right. That's all I wanted to show. Thanks for watching.